Let me begin with a word of prayer. So, sorry to start so late. Dear Father, we thank you for this day. Again, I thank you for this class and this opportunity we have just to meet and study your creation. Just pray that you'd guide our steps today, Lord. In your name I pray, Lord Jesus. Amen. All right, so I'll just very briefly go through a little bit of the solutions here. Not too much to say. Like mission 1, I think you guys mostly got it. Do you guys have any particular questions? So one of the things I put on the announcement was I might ask you to prove the contraction mapping theorem on the test, and I'm not talking about this one. All right, I'm talking about the one I did in class. Okay. All right. So. Oh. Yeah, I'm talking about the fixed point theorem we did in class. I might ask you to prove that on the test. And I said 10 minutes in my announcements, but that was heavily sarcastic. It would take you 20. So.
Wait, so we should know the Banach's point theorem with contraction map?
Yes.
It's not for metric.
Yeah.
Okay.
Right. I mean, I could reasonably ask you something about the homework question, but that was not what I was talking about with more. I'm giving you more certainty on the likelihood that's on the test. Okay. So I don't think I have anything really much to say here. This one, I like the Calc 3 booster question. I'm not sure I can extract a test question from that for this class. I don't know. I feel like problems like the early ones from Nagel, Saff, and Snyder are much more testable and sort of in the major vein of what we've been doing in here, So, and honestly, like, it's really calculus, right? Like it's calculus to analyze the function to come up with the worst case estimator to prove uniform continuity or something like that. And or it's just the geometric series. It's always the geometric series. It's always the geometric series, right? But this would be really hard for me to test because there's epsilon difference between what we're saying and what we're proving. That one was fun. All right, this one, so again, my apology if you spent 20 hours on the first 4 problems. I mean, that's good. I guess I should ask some question on...
20.
Wasn't 20?
No, I just spent
15?
No, it was a lot. It was like 5 or 6.
5 or 6, yeah. So I'm going to post a solution, right? But, full disclosure, I don't trust my solution, all right? There are aspects of the solution which are correct, but are they complete? Not so sure about that.
Oh, wait, which one are you talking about? Mission 3 or Mission 4?
Mission 3.
Oh, Mission 3. Never mind, I spent way more than 6 hours.
Oh.
I know what you're talking about.
So I think the first problem, like problem 20, prove that the quotient topology is a topology, that is actually a very reasonable, decent test question. If you look at it, it's pretty straightforward. That one's not too bad. Problem 21 is so interesting, but it's dreadful for a test question because it's just a mire of notational. Yeah. It's just notational, and I think eventually you get past that notation and just assume that the set and the joint of the set are the same set, and then it becomes easier. But until you adopt that and are able to work through that glib association, it's pain. Problem 22, I'm tired of.
Yeah, that was not fun. I don't remember which one.
Problem 23, I think, was cool. I mean, basically, this problem amounts to saying that the restriction of a continuous map is continuous with respect to the subspace topology. That's pretty much what's going on here. And then likewise, something similar for the product groups. You're forming the multiplication in the product by a Cartesian product of the multiplications, which makes the multiplications of the original groups the component functions of the product multiplication for the product group. But we have a theorem from product topology that if you have a function to a product, that if the component functions are continuous, then the overall function is continuous. See, but that's what bothers me. Is that's not a good question to test you guys on because we didn't prove that in here, and it's kind of outside the course. So, oh well. So sorry, some of the homework is, you know, yeah. That one was kind of fun. Let's see here. I would ask you to carefully study the ones that are linear algebra, like problem 26 and problem 27. You should study those carefully. Make sure you understand those. Those are pretty concrete. Although I will say there was one issue that if it's actually not as hard as I think, I might put it on the test, but if it's as hard as I think, I would leave it as an open question on the test. Which is, it's easy for me to prove that the orbit is a subset. How could I say this? So proving that the orbit is a subset of the points that are a fixed distance from the origin, that's easy. But proving that the orbit is all of the points is not easy for me yet. I was able to prove that it's easy enough to prove that the non-zero vector for the previous problem. Let's look at the previous problem for just a second, and then we'll get to quarks. So this one here, of course, if you have zero, the orbit under the general linear group of zero is just zero. But if you have anything non-zero, you can find any point which is non-zero. You can find a matrix which is invertible, which maps to that point. Let me say this again. Take any non-zero point. Take any other point non-zero. There is an invertible matrix which maps from that non-zero point to that non-zero point. But to construct it, it requires a basis extension argument. This is an important proof technique you should know about. And I do it in here. All right. So I have tried to prove this without this technique before. It's very formidable. All right. So it really rests on the fact that we can take any two linearly independent vectors and extend them to a basis. And a basis, if you concatenate a basis into a matrix, it's an invertible matrix. So the analog of that argument for the next problem, I'm not quite sure. All right, that's what I'm saying, is there's a gap in the next problem. All right, so this one was, the ones about matrices are nice. Now you may or may not know, like the answer to the other one was Jordan form is the representative. Any two matrices are similar if they share a Jordan form. So a natural representative for the equivalence class, where the equivalence is made by similarity transformations, is just the Jordan, or real Jordan form in this context. And these ones were fun once you saw past my typo in my notes. Sorry. Yeah. All right, enough about that. I will show you something else if I can find it. Where is it? If I can find it. Check this out, yo. So this is the homology calculation in homework 4 that I asked you to work through. So this is very helpful. So like if you're calculating the homology of the tetrahedron, you've got your two chains, you got 4 of them, right? There's 4 linearly independent faces in the formal sense of linear independence here, of course. And then you can calculate the boundary map, and you can pick a basis for the different chains involved, and it ends up giving you this lovely 6x4 matrix, and so forth and so on. And then you do some more calculations, you get a 4x6 matrix, you gotta do some row reduction there. There's some calculations to do here, all right? But after the dust settles, you're able to prove what the book asks, all right? So there's a quick overview of the things you need to do that homework problem, all right? But it's good for you to do that. It is a straightforward extension of what we did in class last week. So, all right. Well, with that said, I'm going to shift over and talk about quarks if I can find my PDF. So the last problem in mission 4 is about representing well, what's the last problem in mission 4? You guys should read it again. Some of you haven't gotten to it yet, have you?
It's about the exponential, right?
Yeah, it's the exponential. It's oh man, come on. I'll write it down on the board. Oh no! Oh no! So the exponential of a times d dx, all right, acting on f of x, is equal to f of x plus a. So in this sense, a times d dx generates translations. X maps to x plus a. Now, the proof of that claim is really just Taylor's theorem. Like, what do we mean by the exponential of an operator, like I wrote there? Ay, ay, ay.
A to the n over n factorial, then the n through x.
Right. Yeah. So it's that means like just what you're saying. So we take the sum n equals 0 to infinity of I mean technically it's multiplication by a times the derivative operator, right? That to the nth power 1 over n factorial. But of course that simplifies to, like you just said, a to the n over n factorial times the nth derivative, right? True enough. But in this sense, the derivative generates translations, all right? So there are similar calculations which will show you that other partial differentiation operators generate rotations in the proper context. And I tried to find a narrative to make that all make sense in here, and I just didn't quite get it together for this semester. I'm sorry, guys. But I want to show you some things in this vein, which is like, why do we, like, so let me just ask and answer a few questions before I get too far into this. So we talked earlier in this semester about, and do you guys remember? We had momentum as an operator was like, what was it? I think is it h bar over I, or is it h bar? I think h bar over I, right? Yeah. Partial x. So that's like the x momentum, right? If you were to do the y momentum, it would be h bar over I, partial y, for instance, right? And this is kind of dumb, but like, what's the x? If you want to look at the x operator, what does that do? How do you define the x operator? X times f, how's that defined?
Multiplication on the left by x.
Yeah, just exactly, multiplication on the left by x. So the interesting thing to calculate, among other things, is that if you calculate the commutator of x hat and p hat of x, well, what is that? That is, by definition, x hat px hat minus px x hat. And I'm supposed to I need to let it act on a function in order to understand it, okay? So work that out. Notice that that's x hat h bar over I, partial x. There's an f here, right? Minus h bar over I, partial x of what? Well, x times f. So here, no product rule, but over there, product rule. And so what you got is x hat h bar over I, partial x, minus h bar over I, how's this go here? F plus x partial x, right? And this was supposed to just be x down here. So what happens? Do you see what happens, guys? Some of it cancels, right? So we find a marker here. So we're left with something, though, right? It's not all canceling, and so this piece and that piece, natural enemies, and we get goodness gracious, H bar. I feel like I've lost something.
You lost your negative sign.
Lost my negative sign.
Oh, there should be a prime on it. No, that's all.
Partial x is, I think I get minus h bar over I f. All right. This feels wrong somehow.
I agree with you, but I don't know what you're
Maybe you agree with me, but you don't. You agree with me, but you don't know what I'm talking about. Okay, well, I'll allow it.
I agree, but I don't know what I'm
Oh, okay. You've never seen this before. Well, that's probably a good reason not to know what it's about, especially since I'm being very vague and physicsy at the moment. But so this is the commutator bracket of two operators, which is operator composed with operator minus the same operators composed in the opposite order, right? So to understand an operator, you act on a function, a test function, see what the pattern is. Since this holds for all f, it follows that this is the operator equation which follows. Now, the reason this is a little bit unfamiliar is in my memory, I'm remembering this, guys. X hat with partial x, this is well, minus 1. And so what I'm really thinking of is, I think this one. This is the one that's more natural. All right. But the h bar over I is just an artifact of, well, what is that coming from, actually? It's a little bit, so that's what requires a much longer narrative. So the way we let operators act on functions, well, state functions, all right, like quantum mechanical functions that represent some system, is we exponentiate the operator, right, and we let that act. But so in your homework problem, I kept it easy. It's all real. See, a dx. But in quantum mechanics, you don't just exponentiate. There's an I factor that appears in these for conventional reasons, tying back into the story of the unitary probability stuff that Dr. Schmidt talked about earlier. Like it's tied into that story, right? And so that is part and parcel why there's an I bar here in part. But so outside the context of quantum mechanics, if you wanted to talk about momentum, you wouldn't put the I in. You just exponentiate basically a multiple of the derivative operator. And that generates translations. So in the following sense, momentum generally generates translations, right? The symmetry group corresponding to momentum is translation, the translational symmetry group. Similarly, if you were to study angular momentum, it turns out you can represent angular momentum by rotations. And the symmetry group corresponding to angular momentum is like the rotation group, all right? I'm speaking in a somewhat fuzzy way here, but let me go on. Now, there's a larger point here, which is more linear algebra, to find an eigenstate, which is simultaneously an eigenstate both of position and momentum. What you would need is that the commutator of the two operators is 0. This is a fundamental theorem of linear algebra. You can only simultaneously diagonalize two linear transformations if they commute, all right? So since these don't commute, it's not possible to find a simultaneous eigenstate. And what that ends up meaning is that you can't know with one experiment both precisely the position and the momentum in the x direction at once. On the other hand, it is true that the square of the momentum and the x momentum is 0. It is possible to know like the square of the momentum and the x component of the momentum both with complete certainty. Here's where, and well, anyway, let me go on here. So, so just trying to, I was trying to explain a little bit about why that homework problem's in there. It was trying to make contact with this idea because I'm starting to give you some sense of why it is that we say momentum is the derivative with respect to position, times h bar over I. The h bar over I has to do with quantum mechanics. But really, it's kind of the other way around. So in classical mechanics, you learn that momentum and like advanced classical mechanics, you learn that momentum and position should have a Poisson bracket, which is non-trivial. When you go to quantum mechanics, these Poisson brackets become commutator brackets. And so we know from advanced theoretical classical mechanics that the Poisson bracket of position and momentum should be 1, which then invites us using the derivative as the representative of momentum in quantum mechanics, because we know then it has the commutator bracket of 1. So it's all about representing symmetries, if you can understand it. So let's talk about quantum mechanics a bit more. So this is a very sort of top-level discussion, but that's where we are. Let's see here. So in short, quantum mechanics, you're trying to find a wave function, and it should satisfy this equation with respect to the Hamiltonian operator, right? I times the time derivative of the wave function should be the Hamiltonian times psi. And a symmetry of the Hamiltonian is a transformation which transforms the wave function to like the wave function prime, where you're multiplying the wave function by a unitary operator, right? And that unitary operator has to satisfy this u dagger u equal to the identity, which is sort of the complex generalization of a rotation matrix, right? A unitary matrix. Of course, this is actually a unitary transformation, so it's a little bit more abstract than that. See, because we're thinking actually of, it's a global transformation, which means that we're rotating the fields by different points, by a different amount at different points in principal x. They can have the unitary matrix by which you're transforming the field can vary from point to point in principle here. But you can also generate the unitary transformation by exponentiation of minus I, these parameters, and then these are angular momentum, I believe. Okay, more generally, it's generators of a group. Just context here, this is taken from, most of what I'm writing in here is from this Quantum Mechanics and Symmetries second edition by Greiner and Mueller. And maybe some other stuff from, not so much from this, not so much from Sternberg, maybe a little bit from Griffiths later, but
That's history right there.
yeah. So it's a little old, yeah. Still works.
That's cool.
The physics hasn't changed. Anyway, so yeah, I gave this talk originally in a representation theory class that I should have signed up for, but I didn't. Like, poor professor. He's like, why didn't you sign up for this class? You know, I should have been. I sat in all the classes. After about 2 weeks, I wasn't registered, you know? And I mean, I gave a talk in the class, but I wasn't registered. It's crazy. But I'm a bad student. Anyway, so use a symmetry of the Hamiltonian if the commutator bracket of it is 0. The reason this is important, well, let's look at why that is. So we have I partial psi parm partial t equals to that is true if and only if the derivative of this with that is that. But then what do I do here? There's no time dependence of the unitary operator, so I can pull that out. And so that's that, right? But then, what do I do? To get from here to here, what I do? Oh, remember u times, what did I do? Oh, partial psi partial t is what? It's up here. It was what? This is, I think this is this Schrodinger's equation, or is it? I think it's more or less Schrodinger's equation in the current formalism. Yeah.
Yeah, I've heard it called the time-dependent Schrodinger equation.
That's right, time-dependent Schrodinger equation. So this I'm using in that step. So I trade the derivative with respect to time of the wave function for the Hamiltonian times the wave function, right? Right, so that's what I did here. I traded that for h times the wave function, and I absorbed the I, because that's part of the equation, of the time-dependent Schrodinger equation. Thank you.
And they commute.
But if they commute,
And they commute.
then, well, I can rearrange this to say commutator acting on psi has to be equal to 0, which is to say that the operator defined by the commutator of the operator Hamiltonian and the unitary operator is 0. So this is why, if we want, let me put it into words, what this is saying is that if you do a unitary transformation, right, your new wave function will again solve the time-dependent Schrodinger equation, provided that the unitary operator is one which commutes with the Hamiltonian. That's what's necessary for you to take an equation of motion, if you will, to a new equation of motion. I think of the wave function as sort of a solution to the quote-unquote the equation of motion, although I'm not sure wave functions really move or not. But honestly, if you go watch some interviews with Sir Roger Penrose from the last year, and you will soon, like me, become a believer in the fact that wave functions aren't really well defined. He has some very convincing, very, very convincing arguments that our current philosophy of wave functions is just out to lunch. And Sir Roger Penrose is not somebody who isn't familiar with the problems that are involved. I mean, I'm pretty sure forgotten more about quantum mechanics than I'll ever know. But anyway, he knows a little bit about gravity too, but that's where his real allegiance is. Yeah, but okay. So the set of all symmetries is forming what's called a Lie group, and it has a Lie algebra frac G formed by the generators of the group. The other important ideas for us are that the rank of the group is the max number of commuting generators. G is semi-simple if and only if the Lie algebra is semi-simple. I'm not going to define what semi-simple means in here, but hopefully you'll take a course in graduate school. You'll learn what the proper definition of semi-simple is, all right? But it's a technical thing, as usual. When you're defining something as simple or semi-simple, it's, yeah. That's one of those functorial correspondences I was talking about. Multiplets are G invariant and irreducible, which speaks to the way that the wave functions interact with the operators in play here. So a multiplet of states transforms into itself under the symmetry group. So this is a theorem by Racah. Any semi-simple Lie group of rank L, there exists L Casimir operators, which commute with the whole group, and the multiplets of G can be labeled by the eigenvalues of the Casimir operators, because the Casimirs are constant within each multiplet. So this is kind of giving you a path on how you should label states to be consistent with the structure of the group in play. All right, that's basically what's going on here. So the multiplets are energetically degenerate. If we take some particular wave function in a multiplet, it has the energy E naught, and so Hamiltonian times psi naught is E naught psi naught. And so if we use a symmetry that commutes with the Hamiltonian, and we start with our initial wave function psi naught and rotate into a new wave function psi prime, it will also have energy E naught. That's what this calculation is showing. It still has the same energy. All right, so it is a simultaneous energy eigenstate. Psi naught and psi prime, they both have energy E naught. And that energy E naught is the eigenvalue of the Hamiltonian operator, all right? This assumes that the symmetry in question commutes with the Hamiltonian, all right? Hamilton, listen to me. So let's talk about a particular symmetry and a particular multiplet. One of the most famous early examples of this kind of symmetric symmetry was the proton-neutron symmetry. Protons and neutrons have nearly the same mass. So this is a feature of for us to consider something to have some sort of symmetry group in quantum mechanics. They should be sort of similar objects, and so one aspect of that is they should have very close to equal mass. Protons and neutrons have almost identical mass. All right, they're very close. Anyway, so that means that you can place them in a multiplet, and you can look at the symmetry which rotates neutrons to protons and protons to neutrons. This is called isospin. So like the plus operator takes the neutron and moves it to a proton. The tau minus takes the proton and moves it to a neutron. And you can define, these are actually related to the Pauli matrices. These are the Pauli matrices here. And they have this commutation relation that is somewhat reminiscent of the cross product. These are, rotation type things. But anyway, so tau 1 and tau 2 are this and that, and this is tau 3. So with respect to tau 3, neutrons and protons are respectively eigenstates of isospin eigenvalue 1 and minus 1, which is the next calculation down there. All right. So if we take T3, we act on the proton, we get, oh my bad, 1/2. I can't do math. I forgot there's a half there. My bad. Where'd that half gone from?
Customarily, we rescale these two.
Oh, I can't. Yeah, I should remember these things. So customs I've forgotten aside, we actually have spin 1/2 and isospin minus 1/2 for the proton and neutron. So this is a representation of the Lie algebra little SU2. That's essentially like the tangent space of the identity to big SU2, if you want to think about it in that kind of way. But in other words, you can exponentiate this and get the big SU2. Big SU2 are 2 by 2 unitary matrices with determinant 1. All right. These are not that. They're an algebra of that, which I don't remember the exact structure right offhand, but anyway. So a good typical quantum mechanics notation for this is the neutron. It's got isospin 1/2, and it's in the minus 1/2 direction. The net isospin's 1/2, and it's in the plus direction. All right, so isospin minus 1/2, isospin 1/2. And in this case, t squared, which is the sum of the squares of 1, 2, and 3, is the Casimir operator for SU2, and the eigenvalues are t times t plus 1. These specify the multiplets. For example, 1/2 T3 gives you the n comma p, the so-called iso doublet. All right. So that's not all there was. So early in the 20th century, nuclear physicists also discovered that there were other particles that were colliding together and interacting with protons and neutrons. And they seem to also involve this mysterious isospin quantity. Right? So in particular, you've got the pi plus, pi naught, pi minus. They form an isotriplet. And these are particular nuclear interactions which were observed. You have a pi plus, it collides with a proton, you get out a pi plus and a proton, you get a pi plus and a neutron, it collides, and it creates products of pi plus and neutron and pi naught and the proton. These are all different symbolic representations of particular observations of nuclear physics, all right? People slamming neutrons and protons together energetically. And every last one of these can be seen to conserve isospin. You start with isospin, this has isospin 1, that isospin 1/2, and out goes 1 plus 1/2 again. This one has isospin 1, that has isospin minus 1/2, 1 minus 1/2 is 1/2. This is 1 minus 1/2, which is 1/2, or 0 plus 1/2, which is 1/2. Here you're starting with an isospin of 3/2. You're ending with an isospin of 3/2. Starting with an isospin of minus 1/2, ending with an isospin of minus 1/2. Isospin is conserved, all right? Which suggests that there's some underlying symmetry of physics here. And that is, well, that's the isospin symmetry as it happens. But so that also means that the pi plus, pi minus, and pi 0 mesons define an isotriplet, which is a triple of states which rotate into each other as you operate with the unitary operator that's generated by isospin. As you can see, I wave my hands. That makes it more correct. So it's one of the things you learn as a physics undergraduate. So this brings us to the story of hypercharge. Hypercharge is not charge. So it's also not something my children have, although sometimes, you know. Anyway, so if we examine the isodoublet NP and the isotriplet, these pi plus minus and 0, you notice that there's a certain regularity in the electric charge Q of the states, and we can describe the pattern by, and this is, I guess, Gelman and Nishima maybe introduced this. I'm not sure the exact history of all this, but I know that these guys were involved. So Q, which is the honest-to-goodness electromagnetic charge that you guys, know a little bit about, is related to 1/2 the hypercharge plus the third component of the isospin. So for example, the neutron-proton isodoublet has hypercharge 1. It has hypercharge 1 as it happens, and here's the, you can see, and check it out, see how it works? What's the charge of the neutron? 0, because it's neutral. What's the charge of the proton? Proton, the charge is 1, so we're working in units of, 1.602 times 10 to the minus 19th coulombs, a useless number I know from physics. The electron charge, right? That's the fundamental quanta of charge. Well, for now, not by the end of this talk, though. So the triplet, the isotriplet, all has hypercharge 0 as it happens. All right. So we find that the particles are eigenstates of the charge operator Q with eigenvalues Q. The charges, particles, indeed, the Gelman-Nishima relation reproduces the known charges of the neutron, the proton, and the pi mesons. So this is kind of neat. We've found a description of 5 different particles in terms of some sort of coherent narrative. You're left with the question, why? Why is there such a thing as isospin? Where is this coming from, right? Obvious questions. And this brings us to what is known historically as the particle zoo. So as people were doing these experiments in the early 20th century, like up to the 60s probably, 1920 to 1950-ish, I'm not sure exactly, somewhere in there. Some of these things were done in the early 60s, all right? But we started noticing that there's all these exotic particles, all right? So when you smash stuff together at very high energy, you get these radioactively, very, very unstable particles that radioactively decay back into the ordinary matter that you're more familiar with, like neutrons and protons. Neutron has a half-life of about 11 minutes in the wild. Proton, we've spent considerable expense to try to see if it's unstable, and so far nobody's done it, despite vast efforts, because one of the signatures of all the higher energy speculative physical models is proton decay. So finding limits on proton decay rules out whole theories of physics. And so the Japanese have built these giant underground water tanks to try to look for these things called neutrinos hitting the water, and it makes a particular characteristic radiation, which then has contact with the issue of the proton lifetime. But anyway, I don't exactly know how that happened, how that all ties together. I just know that's the story. Oh yes, we do more of this. So anyway, long story short, these observations revealed that if you organize the properties of the particles as understood in terms of this isospin I was describing to you and the hypercharge I was describing to you, if you draw these pictures with isospin this way and hypercharge that way, all of a sudden you start getting pictures, organizing pictures of all the different kinds of particles you're seeing. You got the meson triplet down here. You've got the isodoublet of the neutron and the proton over here. You've got these basically higher energy states of neutrons and protons. Essentially, these are excited states of neutrons and protons is one way to look at them. So, I mean, like, what are these things? Why are these patterns? Where are these patterns coming from, right? These were open questions in the early 1960s or so. Maybe I'm not sure when these things exactly like coalesced. Probably like late 50s to early 60s is when it all happened. When it was, you know, it took probably the better part of 40 years for all this stuff to really kind of settle. But this was a major event in this story, which was that they discovered this so-called baryon decouplet, where you have these delta particles, the sigma particles, the hieroglyphic particles, okay. And all of this was, all the red stuff was discovered, but this wasn't discovered. So this rather bright individual named Gelman, he said, well, we're going to find a particle down here. There is a particle you can go find. This is, come on, makes a pattern. Like, there's got to be something down here. And it's called the omega minus. He predicted it in 1961. They found it in 1964. That's pretty exciting, really. But it begs the question, why are there these patterns, right? What explains these patterns, all right? And so this ties into really the story of representation theory. And so if you if you have a group and it acts on a vector space, right, then the state vectors form a representation of the group. And then you can study the property of these representations and how they reduce into sub-representations and things. This larger project is called representation theory. We don't teach it at the undergraduate level because it involves both abstract linear algebra and a full and complete working knowledge of abstract algebra. So you put those two things together, you're beyond undergraduate. But it's something every physicist should know because it explains chemistry. It explains why the allowed states of electrons are what they are. All of that's representation theory. Anyway, so these are the representation of the SU3 in terms of these so-called, well, Gelman matrices. And they're Hermitian, traceless matrices, span all such things. The Pauli matrices of SU2 are embedded above as well. Again, we rescale to form something called F-spin. And so you change basis to so-called spherical basis of SU3. Just doing these little sleights of hand here. Notice that the hypercharge is the 2/√3 times the eighth of whatever that thing is called, F-spin. So there are 3 copies of SU2 inside this SU3. SU3 representations can be built from SU2 representations put together. This is one of the stories of representation theory, is that once you understand the SU2, you can use it to build representations of SU3. Now, algebraists who do this, they don't usually work over SU2. They usually work over SL2 and SL3. So if you took a course with my brother, he wouldn't talk to you about SU2 and SU3. He'd talk to you about SL2 and SL3, special linear group linear algebra. So like some of these things are cluttered because the quantum mechanics has introduced these factors of I, and they just kind of flow through everything. There's all these extra factors of I. When you study this as pure mathematics, it gets much prettier, much prettier. But that's not my story to tell here. So yeah, so these are the basic commutation relations in terms of the, these are how the commutator brackets of all those operators I just looked at work. Notice some of them commute, but not all, right? So anyway, so one of the things though you notice is that the hypercharge commutes with T3, which means that we can use common eigenstates to study irreducible representations of SU3, namely of the third hypercharge component, third isospin component and hypercharge. And so like the way this works, T3 operator on this gives us back T3 times the state, and the Y hypercharge operator acting on this gives us back hypercharge times the state. This is like pretty standard quantum mechanics notation, all right? It also drive you nuts when you're a math student taking this stuff as undergraduate. You're like, what does this notation mean? What are we even doing? Just write a matrix or something already. No, they won't. They will only use the bracket notation because it has physical meaning to them. It's not just a notation. It gains a metaphor. It gains like a spiritual aspect to the physicist or something. I don't know. It's whatever. But so if you let T3 and you study this, if you let T plus or minus act on this eigenstate, what it does is it adds or subtracts one value of the third isospin. So you're like modifying the isospin. So this one goes T3 plus or minus 1. That one goes minus or plus a half. This one goes plus or minus a half. And this one leaves the hypercharge alone. This one shifts the hypercharge by plus or minus 1. And this also shifts the hypercharge by plus or minus 1. All of these things put together, we can draw a picture. So basically, if I start with the wave function psi, and I operate by v plus, I go up here. If I operate by u plus, I go up there. If I operate by t plus, I go over there. T minus over there. V minus that way. That way. So these different operators in the SU3 generate these different motions in the isospin hypercharge plane. And you can start to see how we can create pictures like we were seeing. So the multiplets of SU3 are described as follows. SU3 is rank 2, so the eigenvalues of T3 and Y suffice to classify by that theorem of Rakai I was mentioning before. SU3 written in the spherical basis clearly has 3 copies of isospin algebra, which we've denoted by TU and V. SU3 mixes the isospin subalgebras. Thus, each SU3 irreducible representation must contain the TUV irreducible representation. In other words, the multiplets of SU3 are displayed in the isospin hypercharge plane, and they must be invariant under 120-degree rotations. So basically, the SU3 multiplets must be triangles or hexagons in the isospin hypercharge plane. These are the quarks. So the up, down, and strange quarks form a 3 representation of SU3, like this. The anti-up, anti-down, anti-strange form a 3-bar representation of the SU3. And, excuse me. So you can study what are the hypercharge, what's the isospin, and what's the, well, this is called baryon number, and this is called strangeness. These are all just labels for separating different quantum mechanical particles from each other. It's just a labeling system to separate different cases, essentially. I wouldn't make more of it than that. They do have strange names, though, yes. So the up quark has isospin 1/2. It has hypercharge 1/3. It has physical electromagnetic charge 2/3. This is already very weird because it is a known fact of experimental physics that we only ever have observed charge in integer multiples of the electron charge. Fractional charge has never been observed, and this has been tried. So something has to explain how this can be and yet not be observed. That's one of the fundamental challenges for quark physics, is to explain how you can have charge 2/3 and yet never observe 2/3 charge. The answer is something called quark confinement. This is baryon numbers 3, 1/3. So the down quark has like minus 1/3. So the quarks basically have charge plus or minus 2/3 of the charge of the electron. And so antiparticle is like the same quantum mechanical particle, but all the quantum numbers are minus. You know? Notice that like the so check it out, like up quark, 1/2, 1/3, 2/3. Anti-up, minus 1/2, minus 1/3, minus 2/3. See how it works? That's part of the story of the antiparticle. So if you have 2 quarks and you put them together into a composite state, the rules for that, representation theory-wise, is you take the tensor product of the representations. Tensor product of representations is how you fuse particles together in terms of algebra. So the tensor product of a quark and an anti-quark state, it's just like this graphically speaking, and that gives you back the Mason nonnet that we saw. in terms of a high-level description of that, 3 tensor product 3 bar gives us a 8 plus 1. That's the, so you've got the nonette plus this eta prime particle. So what about neutrons and protons, right? So that's the recipe for pi. So if we take, if we put 2 quarks together, we could do that also. Rather than the quark anti-quark, quark together, we get this. Maybe this was the meson. No, this. What is this? I don't know its name. Anyway, we get this. I don't know if these are observed or not. These may not be observed. I don't think these would observe. I think these have fractional charge. Yeah, these are not observed. This is just a midway point, calculationally. All right. So that's what we do. Take 2 quarks, put them together. What if you take that and then you tensor product with a 3rd quark? Right? So actually, yeah. So now we take 3 quarks. So the 2 quarks from the previous slide and now the 3rd one. And that gives us this picture, which gives us this, which I've made little circles to indicate there's 2 there. And there's 3 in the middle. So you get this triangle and also this. And so these different particles would be formed by like a down, down, down quark, an up, down, down, at the bottom, strange, strange, strange. Right? Those are just different ways of combining the quark states. Right? Take 3 quark states, put it together, you can generate this pattern. And that exactly matches with the observed decouplet, including the recently 1964 found omega minus, as well as these. And this, mathematically, so if you have 3 quarks, you put them together, you can get this 10 plus this 8. And baryons include like neutrons and protons. Baryons are basically hadronic matter, which is made from 3 quarks. So while people have never directly observed a quark, this is why we believe in them. Because simply positing the existence of, you know, the up-down strange quark and their anti-quarks paired with the well-defined mathematics of representation theory, which, by the way, has been incredibly successful in predicting all of chemistry. Understand that, like Dr. Skambordis has spent semesters studying representation theory out of a book called Hammermesh. Not because he's a high-energy theoretical physicist, but because he was very interested in like atomic and molecular physics. All right, so all of these theories have cut their teeth on far less esoteric things. All right, it's very conservative, very well understood mathematics. And so you apply that to this, you know, this conjecture that there's these quark states, and you can produce observed patterns for the neutron, the proton, and this host of other exotic particles that you only know about if you run high energy, you know, nuclear experiments. But the interesting thing is, so there's this. This is sometimes called rats. So there's a couple different notions about SU3 floating around. So I told you guys about like SU2 symmetry. Remember I talked about this the other day in here. I talked a little bit about like SU2 going to like electroweak gauge theory. So electroweak gauge theory, there's protons, there's also the W plus or minus, and the Z, what are the names? Bosons. These are the force-carrying particles for the electroweak force. In our current energy, there's electromagnetism and there's the weak force. The weak force is incredibly short range because the W plus minus and the Z bosons are massive, whereas the photon is massless, so it has infinite range. The similar story for what I'm talking about here is the so-called color force, and that has to do with an SU3 gauge symmetry. This is sometimes referred to as QCD. When you look at the quantum mechanics of it, QCD is for quantum chromodynamics. The chromo is color. And so we're talking about, it's just a label. These quarks, what I'm trying to tell you is this SU3 is not exactly the same as that one, but they're related. And in principle, so this is like, there's like a principal fiber bundle, and you can study like, gauge connections, all that stuff, and ultimately like how to do quantum mechanics over all that and develop the quantum field theory. So from that, you can write down something called a Lagrangian. And in principle, you ought to be able to derive certain bound states, stable states, right, which have the properties of the quarks. There ought to be a way to derive the quark states from the QCD Lagrangian. As far as I know, this has still not been done. So we have this interesting state of affairs where we have descriptions of like the basic physical equations, right? And we believe in the existence of these quark states, but we don't actually know the mathematics of how these things can be derived from that. Like if you could derive the quarks, if we could derive stable states of quarks from the QCD Lagrangian, I'm pretty sure you'd get like a Nobel Prize. Well, Nobel Prizes are only for people who do experiments, but you would probably have a Fields Medal. I don't know, you'd have the respect of people who care about things like these, but anyway. So, so here's some confessions and conclusions. Quarks have spin 1/2, whatever that is. And these are fermions, which means they must obey the Pauli exclusion principle, and I've completely ignored that in this talk. So everything I've said is schematic. Everything has to be passed through that filter of creating states which satisfy the spin statistics theorem. And this is what I was just talking about. We have been talking about SU3 flavor, which is a global symmetry. So the flavor symmetry puts guidelines in the overall particle content. It has no dynamics. On the other hand, SU3 color is a local symmetry, and it should have a dynamical, it has dynamical fields. The quanta of the SU3 color symmetry are called gluons. I know, it gets weirder, doesn't it? So like, you've got these W plus minus bosons. The force carrying particles for the color force are gluons. They glue the nucleus together, right? And the weird thing is they can glue each other together, and so they form these things called glue balls. Do you know if they've been observed yet or not? I don't know. There's also something called a quark gluon plasma. You guys have been taught there's 4 states of matter. It's not true. There's something like 19. In terms of like studying decoupling of different energy, energy. Basically, it's a different state of matter if you have a phase transition. And so there's like a jump between where you are and where you're going to, like with water versus ice, with gas versus liquid. Plasma, we know, maybe you've heard of plasma as the 4th state of matter. It's when the electrons are what? Microwave. Oh yes, we heard in the microwave. So the electrons are decoupled from the atoms, right? The electrons, there's just an electron sea. They float about. They're not, the electrons are no longer linked to the molecules that they're from, right? And so as you get into higher and higher energy and higher pressures and things, you can uncouple other aspects of matter. And as you do that, and you understand things more deeply than I do, I've heard the number 19. It may be higher by now, but.
Well, depending on how you define things, or even, I was looking out, there are 21 known phases of ice.
21 known phases of, oh yeah.
Solid, but there are different crystal structures, and they have these transitions.
Right. Yeah, yes, okay, so that's another direction to, that's another direction to nuance things for sure. Yeah, this is, but like, anyway, yeah, there's a lot to say there, but yeah, so that's my talk about quarks. So I hope you enjoyed this semester. Is this our last? I think this is our last class, isn't it?
Yeah.
So sad.